And what we have written inside this, it is g of n. What is g of n? G of n is what? Function. So this operation is done repeatedly, comparison operator. We already discussed the case efficiency. It can be best case, worst case, another one is average case. So again, algorithm we have directly taken f of n. What are these? These are the comments for us to read, for us to understand. Hello everyone, myself Evelyn Jacob, working as a faculty in BCA department, Vidhyaashram First Grade College, Temple of Excellence, Mysuru. So today's session, we'll be discussing about the second unit in the subject, Design and Analysis of Algorithm. So it is unit 2. So unit 1 we have already discussed. Now we'll discuss about unit 2. So what are the topics covered in the unit 2? So in this topic, the very first topic is asymptotic notation. What is this notation and why it is used? What is the definition of it? Next, the introduction. So if I say asymptotic notation, what are the types? So these are the types of asymptotic notation. Then we follow with the algorithm. One is the recursive and another one is non-recursive. In that, what is mathematical analysis of both recursive and non-recursive? These are the topics covered in unit 2. So, what is asymptotic notation? The very first definition. Why it is used? So, we can see the definition. It is also a notation. What notation? Mathematical notation. It is used for analysis of algorithm. It is the mathematical notation used to describe the running time of algorithm. See, for an algorithm, we may give input. The input size may be low or high. Depending on that, we'll decide what is notation and why it is used and how it can be found. Asymptotic. The word asymptotic is a Greek word, which means not falling together. Okay. So, see, when we take the execution of an algorithm, when I run an algorithm, it depends on what are the factors. First, it depends on the instruction set. So, if our code is lengthy, it will take more time to execute each and every statements. Then the processor speed. What processor you are using? Sometimes the speed will be very low. Sometimes very high speed. So, it depends on the processor speed. Next, the I/O speed. Like that, many other constraints for the execution time of the algorithm. Okay. How to estimate all this? So, we estimate the efficiency of an algorithm asymptotically. Okay. Next, then how to derive an equation? If suppose I take T of n and G of n, it is any non-negative function. It is a function, but it is non-negative. Say I can say any function, say phi n plus 10. Okay, this is also function. I'll denote it as T of n. It should be a non-negative function. Next, the algorithm running time T of n. See, suppose if T of n is the running time, it is also indicated by its basic operation. Say for the add, what is the basic operation? I'll use plus. So each time I'll add, say 2 plus 1. So plus will be the basic operation. This is used in an algorithm. This will be helpful to calculate what? The efficiency of the algorithm. Then, as you know, if C of n is the basic operation count, we denote C. C is the count. Count of which one? It is the basic operation. Then what is G of n? I'll indicate G of n as a function. We indicated T of n as the T means time. What time it is? Running time. Then what is C of n? C of n is count. Count of what? It is a basic operation count. In our example, we took add. Add is the operation. Next. Then what is G of n? G of n can be any function. Then what are the types of asymptotic notation? In this, you have 3 types. What is the first one? Big O. It is not just O. it is big O. Then this symbol is omega notation. What about this? This is theta notation. In your exam, if they ask, list the types of asymptotic notation and explain, you have to list it and explain with a graph. So why this asymptotic notation are used? Now we'll use to find the running time complexity, or we can say efficiency of an algorithm is used asymptotic notation. So what are this notation where we can use? For the next slide, we'll come to the introduction of it. So how to denote this? We know it is big O. And what we have written inside this? It is g of n. What is g of n? G of n is what? Function. We say is the set of all function with a lower or same order. With a lower order, we can say it has lower bound to upper bound. So lower bound is, if I take an array with a base index 0, if I take 100 elements, my upper bound will be 100. This is what we say as lower. Next. So this is an example. What they've said is, if my function big O of g of n does belongs to any function. With this example, we can tell n belongs to big O of n square. What is n square? See, when I say power 2, it is nothing but a polynomial function. When I degree of 2, it is quadratic function. Okay, similarly, you can say another example, 100n. 100n plus 5 belongs to big O of n square. So these are the example. Each example, what we do is, we give us notation, say big O, and we say it belongs to so and so notation. Next notation is omega. What does omega notation will do? This function will have higher or same order growth. The order of the growth may be same or it may be higher. So then how to denote this? This can be denoted by a function, say n cube. We'll say it belongs to omega of n square. So here also you can say it is a cubic function. To the power of 2 is nothing but a quadratic function. Next, the last one is theta of g of n. Then what is this? This is also a function. Which function? That is g of n. It's also a function. It can have the same order of growth. So the order of growth we have already discussed. What is order of growth? We also denoted, say, by big O of, say, 1 less or equal to, this symbol was there, right, till big O of n factorial. This is the order of growth. How the order of growth changes, it depends on a program. Next, here we had given an example for quadratic function. Directly we had given that is 2. To the power of 2 means it is quadratic, or you can say it is a polynomial. an square plus bn plus c. What is a? A should be greater than 0. Then if it's in theta of n square among infinitely many others. So what they've done is, they've taken a quadratic equation and compared with what function? Theta of g of n. Next, now we'll go in detail with this graph. So I told you, right, whenever they ask question regarding asymptotic notation, you have to explain with graph and the example. This is very easy. You can take some function and we can write this graph. So how to start with? First one is big O notation. Say again we'll take a function. What function? T of n. You can take any function, say f of n, g of n, anything. So we'll say this function is big O of g of n. How to denote this? We'll say t of n belongs to big O of g of n. So my function, it belongs to what notation? Big O. Then if there exists some positive constant, we say there is a positive constant for that time and it should be a non-negative integer. That non-negative integer is denoted by n0. Okay. Next, what is the function is? So t of n is a function, is less or equal to c of g of n. C is a constant, g of n is a function. For all n is greater or equal to n naught. This is the equation to tell it is a big O notation. So when you see this graph, what it tells is, see, big O notation t of n, same what we said here, it is repeated. You have to write down like this, t of n belongs to big O of g of n. There is a graph, say there is a n and n naught. And you can see this is a t of n. The graph is being plotted here, that is t of n. There is only one constant, so c of g of n is taken. So this is it doesn't matter. It is simple graph which illustrates about big O notation. Next, coming to what symbol is this? This is omega notation. Again the same old concept, but some constant might change. We'll come to this. So function t of n is said to be omega of g of n when my t of n belongs to which function? Omega of g of n. Next, what is t of n? T of n is bounded below by some positive constant. So it should be a positive constant. If there exists some positive constant c, so c, if c is a positive constant and some non-negative integer n naught. So n naught is what? Non-negative integer. What is c? It should be what constant? Positive constant. Again this function lies. So what we can say? T of n is greater or equal. Okay, see the difference? Greater or equal to what function? C of g of n. For all n should be greater or equal to n naught. So this definition is illustrated in this figure. So this is big O omega notation. So what happens is same graph but slight change here. This is n is there and t of n, c of g of n. We have compared with greater or equal to. So here you have a plotted graph here which indicates doesn't matter. This is all about omega notation. And coming to the last notation of asymptotic, that is theta notation. So when the function is said, t of n is said to be theta of g of n, is this function t of n should belongs to big O of g of n. So what is t of n then? It is bounded above and below. What is above here? We can say upper bound. So in the theta you can see the difference. You have upper bound as well as lower bound. I already told now what is upper bound in an array, the last element. Lower bound is the first element. Then there exists some positive constant. You can see two constant are there. Why two constant? We have upper and lower bound. So this is C1 and this is C2. Okay. And there is some non-negative integer. Which is a non-negative integer? N naught. How the function will be? This is the function. What is the condition? C2 g of n should be less or equal to t of n and t of n also will be less or equal to C1 of g of n. What is the condition for all? N is greater or equal to n naught. So this is illustrated here. So you have two constants. Previously we had only one constant. We used to tell C of g of n. But here we have C1 of g of n and C2 of g of n. In the middle we have t of n. See, you can see this. In the middle it was t of n. So that is why in between C1 of g of n and C2 of g of n, you have which function? T of n. And this also we already know that this function belongs to theta of g of n. This is also same thing. No changes there in all the three notations. So it's very easy. The one thing you have to denote this and tell what are these, what are C1, what are C2, what is this function, and can write this figure. These are the three types of asymptotic notation. So when we finish this notation, now we discuss about the mathematical analysis. For first one, we'll discuss about recursive and non-recursive algorithm. So in both the things, if you say recursive and non-recursive, first we should know what is recursion. Then what is non-recursive? Recursion is, we already discussed, if a function call itself. The very first example I already used is factorial. Okay. If I take a factorial function, I'll write some code. Say if my n is equal to 0, return 1. So meaning to say, if I give a 0 number, factorial of 0 is 1. Else I can call again the factorial, same old function I'll call, and with other properties. Say I can say n minus 1 or into, I'll call some code. So the function called by itself, it's called recursion. If I don't want to call this recursion, what I do this, I won't write this factorial. That is non-recursive. I just write a code. I don't call the function again. So how to write in this topic, we'll discuss about this mathematical analysis, how to write an equation for it. So there are some steps to follow. What are the steps? We should count the number of basic operation. So any algorithm we write to do some task. Operation can be anything. It need not be always add. It can be anything. If I want to sort, I need to compare all the elements. My first element, if it is in ascending order, my first element should be always lesser. So this operation is done repeatedly, comparison operator. So we have to count the number of basic operation. So how many times this operation have been executed? If it is in a for loop, say I less than 10, how many times this comparison will be done? 10 times. Okay, that is the count. Next, loops will become series sum. So that loops will be denoted by series sum. It can be denoted by sigma. So you need some series formula. So based on that operation, based on this step, we'll denote by formula. So we'll take an example for maximum. What is maximum? If I take number of elements in this, which is the highest. So maximum element is nothing but highest. So the very first unit we discussed how to write an algorithm. In order to write an algorithm, I have to use the keyword algorithm, that is reserved. Then I should use what? Algorithm name. This is your choice. You can write anything of your choice. Then in the parameter, I'll denote what? Input. Say my input is A is a array. So array elements from 0 to n minus 1. Next, I will denote my first element as max value. I'm analyzing. Maybe my first element will be the highest. Then why this operator is used? This is nothing but assignment operator. Instead of equal, I will write left arrow for the algorithm. Next, for this I have to write a loop. Since there is more than one element, I'll run a loop. Which loop it is? For loop. For I equal to 1 to n minus 1, do. What should I do? I should keep on compare. Which should I compare? I'll compare my A of I with the max value. What is max value? First element. I'll compare my first element whether it is max value. Okay, if it is greater, then the A of I will be highest. I will assign to max value and return what? The max value. Now we have to analyze this algorithm. See, one thing we should understand that if my input size is less, say for your lab programs, you may give 5 or 6 elements. In that 6 elements, you have to find what? Highest. That is maximum. So, to generate a maximum value from 6 elements, it does not take much time. When I give some 10,000 elements, it's time to analyze its efficiency, right? So, how to analyze? First, we have to denote what is the problem of the input size. Say my n will be, according to you, it may be 5 or 6, but according to a real-time application, it is not a single number, it is more than that. So, say 10k. Next, most frequent operation. In this algorithm, what is the most frequent operation? This is greater symbol. This is the most frequent operation, right? It is what? What operator it is? It is comparison operator. Next, we have to analyze the cases. We already discussed the case efficiency. It can be best case, worst case. Another one is average case. So, what is my best case? Best case is if my first element is highest, it is the best case. What is average case? Average case, I can assume average means something in the middle. My middle element was the highest. That is the average case. Then what is worst case? My last element or last but one element may be the highest. So you have to assign everything, every scenario. Every time it can't be best case, every time it can't be worst case also. Then if I denote C of n is equal to number of comparison. See how many times the comparison operator has added in the loop. Then I'll denote with a mathematical analysis with the notation sigma. How shall I write this? C of n is equal to sigma of I is equal to 1 to n minus 1. That belongs to the notation used. So, now how to write a plan. This is a general plan for analyzing the time efficiency of non-recursive algorithm. We'll write the code in a function. We don't call it itself. That is non-recursive. So first, what is the plan? We have to decide the input. What is the size of the input? When you run the program, very first program is selection sort. Decide how many inputs shall I give? How many number of elements should I sort? You may give 8, but 8 is too lengthy, so I'll decide don't want 8, I'll erase it and make it 6. So you have decided what is the input size, it is 6. Now, after giving 6 input, now we'll give the elements 6 elements. That is what it indicates what? Input size. You have to decide what is the size. Next, you already know this. What is the basic operation? Every time comparison won't be, it can be other operation also. According to our algorithm for max element, it was greater symbol. That is our basic operation. How many times it is executed also come into a picture. First, we have to identify which operation is done frequently. Next, we have to decide number of times the basic operation is executed. I told for 6 elements, 6 comparison have to be done. My basic operation is greater symbol and how many times it is executed? 6 times, right? Next, we have know what is the input size and how many times the basic operation is executed. Now we have to analyze the worst case, average case, best case too. Best case, there is no need to analyze because best case, we don't need to generate a mathematical sum of it. Best is from 1 only we get. Okay, what it takes time is, it takes time for the worst and average case. So now, it depends on some additional properties for worst case and average case efficiency. Now we have to, once we have analyzed all this, we have to denote with the equation, say sum, say sigma. Okay. Next, with the standard formulas and rules for this manipulation, we establish the order of growth. Once we analyze, we denote the formula. Why we have to denote the formula is for the order of growth. See, from the third unit, after every sorting or searching, after every algorithm, we'll implement time complexity. For some algorithm, it can be big O of n. For some, it can be big O of n square. So when we come to the third unit, we'll discuss how this complexity has arisen and how to denote this. Told that it is denoted by asymptotic notation and we had gone for the big O. Next, we'll come across the algorithm. We discussed about non-recursive. Now it's time to discuss about recursive algorithm. So what it is? When I say recursive, I told it should call again. The function code will be returned. Again, if it call, that is recursion. So what example we have taken? We have taken a factorial. So again, algorithm, we have directly taken f of n. What are this? These are the comments for us to read, for us to understand. It computes n factorial. Okay. If I say 3 factorial, what is the answer? First, I'll take this number, I'll reduce by minus 1. 3 minus 1 is 2. Again, 2 minus 1 is 1. So, until 1, we have to multiply. 3 into 2, 6. 6 into 1, 6. So, if I say 3 factorial, what is the answer? 6. So, whenever I want to give an input, it should be what? Non-negative. I should give a positive number. Next, what is my output? The factorial. The factorial, n factorial. 3 factorial, that is my output. So first is a condition. What is a condition? If n equal to 0, for 0 factorial, the answer should be 1. So return 1. If it is not 0, what you have to do? You have to say return, again call this function. What function? F. I can give a fact also. If I see f, I don't understand what is f. I may think it's something function. So what I say? I say fact, and what arguments I'll give? I'll give n. So I told now this function, it depends on you, whatever name you can give, but you should give this keyword. This keyword should not have any spelling mistake. So what I do is I'll call the function, say fact, and each time what I should do? I should minus 1. Say 3 minus 1 will be 2 into n. Into my n means the what value you had given, that. So this will tell you it is a recursion. The moment I see this function calling again, this function only it is calling again, I say recursion. So how to consider this? So in this, you have f of n. So f of n is computed according to the formula. When we finish this factorial of recursion, even here you have some mathematical analysis. Based on the operation we have to consider, then we have to denote the sum of its expression. Next. So now how to analyze the recursive algorithm. So we have already discussed, again we'll have a revision of it. So first time it denotes the input size. What input size we give. Suppose 6 elements are there or 5 elements, depends on whatever input you give. Next, it identifies the basic operation. So in my factorial, what was the basic operation? It was multiply. Each time I will multiply it. Next, again we have to consider what? Best case, average case and worst case. So till now, that was the 3 operation that is common to both recursive and non-recursive. But when I come to recursive, what are the other steps? So with this recursive relation, we have to consider the initial condition. What are the number of times the basic operation is executed? Okay, number of times. That is also similar, but we have to use recursive or recurrence relation. Then we have to solve the recurrence. Then at last we have to, why we are doing all this? To find the order of growth. What is the order of growth of algorithm? So it can be big O of log n, logarithmic of n. So depend on the algorithm, at the last step will be the order of growth. So that's all for the today's session. For the next session, we'll be discussing about Unit 3. Thank you.